Well, yeah. See, that was. So, I mean, with World War I, like they were drafting and getting anybody that could fight.
I would figure he would get like immunity or something.
Yeah. Not.
Well, after he got killed, they changed the law.
Yeah.
Oh.
And to where, scientists and smart people didn't have to go to war.
Too late.
Yeah, a little bit too late for him. Yeah.
Yeah.
So yeah, I guess that was after World War I then. So
Yeah,
that makes sense.
it was 1915, I think, is when he got killed,
Yeah.
or something like that.
Yeah, secret workman. But the whole war was kind of unfortunate in a nutshell. So. But yeah, is it recording? Oh, it is recording. Awesome, thank you. All right, so we are going to go over these notes and how we fill these in. So let's start off with this first one. Dmitry Mendeleev, the first person to arrange known elements in a systematic way, according to what? What do we have for this one? Or what did y'all use for this one?
I put properties, and I also put properties on the third.
Yeah, see, this one was weird.
Atomic mass.
You put atomic mass?
Yeah.
All right. You put atomic mass, yeah. So you're both right. All y'all are right. And the way we worded these notes are a little weird, but they're both correct. He ranged them. So he's the first one to range them by properties, but more specifically physical and chemical properties, right? And then when he got those properties together, he used the atomic mass to arrange them with those properties in mind. So, right? So that's what I was saying, because I was taking a quick glance at y'all's answers beforehand, and I was like, oh yeah, I kind of almost figured that that would happen at some point, because it was a little vague. Even when I first looked at it, it was a little weird. But yeah. So let's go on next. So he left what? Because no known elements fit his patterns.
Space.
Spaces. Is that what I'm saying? Blanks. Yeah. What do you like left blanks? I like blanks a little more than spaces, personally. Can't spell blank. There we go, blank. Or blanks, multiple. Because no known elements fit his pattern. Yeah, but he ended up being right? Like a lot of those ended up getting filled in at some point because other people discovered them. So let's move on to Moseley here. All right, so what was Moseley able to determine?
The frequencies of corresponding lines in an X-ray.
Frequencies of corresponding lines in X-ray. More simply, like what did he do with those X-rays? And what was the reasoning behind the frequencies that he found? His experiment. He just did a thing. So he's the one that actually found out he's the one that determined the atomic number of an element. And that was because of those experiments. So he found that he had an atomic number plus some constant, or he found the atomic number, and then he noticed that with those X-rays, they had increased frequency based on that number plus a constant. So that's how he was able to determine the atomic number, and that's he made the term for atomic number, but we now know what does the atomic number represent?
The amount of protons.
Yeah, number of protons, right? But that was one of the main purposes of the experiment and how he related that. So, I hate that it says determine the atomic number, but I think he came up with the term atomic number and how it related. So, we'll go into that in a minute. Atomic number. What else do we put in here? The elements. Alright, so yeah, mass and coding, yeah, you already got these elements. Perfect. did you get, did you fill in the first half here with Dimitri? We're just talking about the initial part,
Mhm.
the part A? Okay, cool. Just let me know if you have any questions on that. What did you end up?
What's the first one?
Here, let's just go down and go ahead and quickly do that.
Physical.
Just because it won't take too long, right? So first person range known was a systematic way according to, this one's physical chemical properties, and then this one is,
Atomic mass.
yeah, atomic mass, thank you. It was weird because it was worded pretty similarly, but he ranged it by physical chemical properties, and then from that used the atomic mass to organize it. And he left blanks because, you know, no known elements fit his patterns, but those elements in the beginning found it. So let's go back, line this up right. Close enough, right? Yeah, there you go. So the higher the atomic number of the element, the shorter the blank with the X-ray that's produced, right? So what do we think on that one?
Frequency.
Shorter the frequency?
Wavelength?
Wavelength. So I have wavelength, right? Because frequency. So do y'all remember what does frequency directly relate to?
Energy.
Wave indirect.
So I heard energy, right? So does it make sense that the higher the atomic number, the more energy that's going to be given off by the higher and higher elements,
Yeah.
right? So if we had a higher frequency, that means we have a shorter what? Wavelength, right? Because they're indirectly proportional. So that was just how it's worded on here. I think in the article it talked about frequency. I don't think it talked about wavelength, but I thought that was a neat way to reconnect everything. So you never forget. Never ever forget. So yeah, it's a shorter wavelength, right? Right? So he arranged the elements in order of increasing what?
Nuclear charge.
You have nuclear charge. Anybody else? Anything else? Anything more increasing protons? Atomic number. So, just given what we just talked about, I would think maybe atomic number, right? Because we were just talking about that, right? But you did raise an interesting term with the fact with the nuclear charge, and we will actually be talking about nuclear charge in the future because it's important for ionization energy, right? Do you remember the definition of nuclear charge off the top of your head since you put down, or you just put down?
Like the charge of the nucleus?
It's like, yeah, it's essentially like the charge of the nucleus, or essentially the effect of the nucleus on like an electron on the outside, and we'll go into exactly what that means when we go to ionization energy and how that affects ionization energy. But it's an interesting term to bring up right now, so just something to think about, I guess. And then periodic law, when elements are arranged according to Apprecia's atomic number, there's a periodic retreating pattern in the element's chemical and physical properties. That's already in your notes, but that's just talking about periodicity and what that means, right? It's just that when you arrange it like we have here, you're going to have repeating patterns as you go down. Alright, so let's talk about the modern periodic table. Horizontal rows. Alright, I didn't even put it on here, sorry, oops. Increasing atomic number. So yeah, I use atomic number. You're technically right with protons, because protons, same number, atomic number, but you know, I just like using the term a little bit nicer. Alright, modern periodic table. So down here, what are horizontal rows called? What are they called? What do we call them?
Periods.
Periods. Okay, so periods. I don't know if we ever talked about the other way, the other name. But they can also be considered series as well as another thing that will be thrown around. But periods is the one we use most often. So yeah, don't worry if you didn't get series. I mean, we really haven't used series in here, but we've definitely used period. So vertical columns are called what?
Groups. Or
Group
families?
or families. Yeah, groups or family.
Were the notes were already due or they due today?
They were due today
Not turned
before
in.
class, technically. If they're not turned in, if they weren't turned in, I'll just count on like 8 points.
Well, I turned it in, but like some of the answers aren't right.
Oh, no, that's fine, yeah. I just want to see that you did it, because
Oh,
the
okay.
point of today is I wanted to, get everybody's answers together and talk about it, because I thought that'd be more fun with the fill-in notes rather than just me telling you what to fill in, So, yeah, and I'm only checking that for completion, really, or so. So, yeah, vertical columns are called groups or families. Okay, so elements within a group have similar chemical and physical properties because they have similar what's?
Valence electron.
Valence electrons, any other answer on one? No?
Some electron configuration.
Electron configuration. And yeah, you're both right on that. The notes specifically, because they have a similar outer shell /valence electron configuration. So yeah, they have the same number of valence electrons, they have the same electron configuration, and that's why they have similar properties when you go down the periodic table. So yeah, so I'm going to put down specifically just similar valence electron configuration. We're comfortable with the term valence, right? Cool. So we'll do valence. Can't spell valence. Apparently I'm not comfortable with it. Alright. Some groups have special names. So we went over this in the activity with the coloring sheet activity for the periodic table. So group 1A or group 1, what is the name of that group?
Alkaline metals.
Alkaline metals. Awesome. What is the name for, I think I should probably write it down for the video's sake, just in case. What is the name for group 2?
Alkaline earth metals.
Alkaline earth. Yep. Or alkaline earth metals, excuse me. There's a little bit of difference. Group, this is, I think, 16, yeah. Nobody knows, but that's good because we didn't go over this one. But this is something that not many people teach. We're going to teach it here. And like I said, even the worksheet wasn't there. It is a little bit of a weird name. It's called a chalcogen. Oh gosh.
Shallow.
Chalcogen.
Chalcogen. Yeah. Chalcogen. Chalcogen. In fact, it's something that I never even learned, even with my college as well, but it is the name of group 16 that we can use. That was something I learned when I got in here. Mr. Hobbs gave me another one of his fun facts.
Yeah. Okay, they're called chalcogens because most ores of copper, and the Greek word for copper is chalkos, are oxides or sulfides. So such ores, traces, selenium, tellurium, atomic properties of the chalcogens.
That,
So,
I can see it. That makes sense. That's weird.
you're in a very elite group of people
Yeah.
in the world that will know the name of that group.
Alright. Back to things you probably do know. Group 17 here. What is that? Halogens, yeah. Alright.
Noble gases.
Noble gases on group 18 here. I guess it really isn't blank, but I guess it might have been another page, I'm not sure. Alright. Just a few groups there. Alright, we're almost to periodic trends. Yay, periodic trends. Alright, so elements can be classified into 4 categories using, according to their electron configurations, right? So let's start with noble gases. So their S&P orbitals for noble gases, what are they, what did we put down for this one here?
Full.
Complete.
Complete, full, somebody say filled maybe. Same difference, right? So I'll just say that they're 100%, they're filled. So we know it's a filled octet, right? So they're super stable, right? So what does that mean about their chemical reactivity?
They don't bond with other.
They're unreactive.
So yeah, they're unreactive, they don't bond with other elements usually. Now it's always important to say usually because
Yeah, 'cause they
there are very few exceptions, but they do happen. But more than likely, they don't. Like the exceptions usually happen when it's like a super big element because then the rules get a little looser, right? Like something like xenon, for example, like you'll see a xenon tetrafluoride sometimes. It's not very useful, but it's an element that can form, and that's only because it's like so big that a lot of the times the electrons are so loose on the outside. But we'll get into more of the trends a little bit later. But generally, though, they're chemically unreactive. So we'll say that. Right? Representative elements. Elements whose outermost S and P suborbitals are only what?
Partially full.
Partially filled.
Partially filled? Yeah, partially filled. So they're the group A elements that we're talking about, but again, that's an old convention. So if you want to do this, you can like always like cross this out and put like, 1, 2, and then 13 through 18. If you want to do that on your own time, and if you want to just give yourself a reminder, right? Because that is an old system. These notes are before we just started using 1 through 18. But yeah. So the group number tells us what about the representative elements?
The amount of valence. Amount of valence electrons.
So amount of valence,
Oh,
what did you
yeah.
say?
Yeah, no.
Oh, you
yeah,
disagree with
that's-
them. Okay, yeah. That makes sense. Anything else? Anybody else? Any other questions or answers for this one? No? Alright, yeah. So number of valence electrons. Alright. Alright, so transition metals. Elements whose blank sublevel is only blank. What sublevel is it first off?
G.
D sublevel, yep. And then, what do we put in the blank?
Partway full.
Partway full? Yeah, I'd say partway full. Sometimes they're full, if you're using like the one at the end, but yeah, partially filled. Ooh, I am not writing that well. Can y'all see that says partially filled? Okay. Classified as group B elements, again, we don't really use that convention. If you want to, you can cross that out and put like 3 to 12. Just to give you a reminder, just in case. They have a wide variety of properties. So, inner transition metals / rare earth metals. Elements whose blank sublevel is only blank. F, partially filled, right? So, these are the bottom 2 rows, and I think I mentioned talking about this earlier, because you're asking like, do the lanthanides and actinide series count as metals? And yes, they do, and that's one of the, we can use this name for them as well. So lanthanide actinide series could be considered rare earth metals, or the inner transition metals. But yeah. So that's just to give you a little bit of clarification on that, because I know I mentioned that, but I didn't really say what it was, what the names of those were. So actually, if you want to, and I don't think they do mention that, okay, cool. They do mention it down here at the end of the notes, but, yeah, so ignore what I was about to say. So I'm going to move it up here, and erase all of this. So bottom 2 rows, element 58 through 71, what is that?
Lanthanide.
Lanthanides. And then elements 90 through 103.
Actinide.
Actinides. I think that's how you spell it. I'm gonna check. Some really bad stuff. Actinide. Okay, yeah. Did it spell right? I don't know if I did. No, I did. Okay, cool. Still struggle with English to this very day. So, now we're on periodic trends. We've gotten through everything that, why the periodic table is arranged in the way that it is. So now we're going to talk about the actual properties that we've been talking about why the periodic table has been organized. We've been talking about how the periodic table is organized by properties, and now we're actually going to talk about said properties, right? So, go ahead and pull up your graphs here, right? Go ahead and pull up that assignment, just so we can talk about them. And I have some visual aids as well that we can use for these. But it's good to go ahead and have your own work here, right? So, first off, let's go ahead and start filling in some of these. So, atomic size / atomic radius. Do you have like a decent definition for this? What do we have for this one?
It's like how far apart the
like
electrons are
half
from
the
that.
distance between the nucleus and the outermost
Yeah.
electron coil.
Something like that. Essentially, you're talking about the distance from here to here, right? Because it's a radius, right? We're talking about radius, you know, it's half the diameter, right? So you have your nucleus in the middle, wherever the end of your electron body is. That's a good definition for it. The one that we have here is just half the distance between two similar atoms of a diatomic molecule. So that's just saying, essentially what we were saying. So I'm going to write that definition down here too. But you have the definition that you were given on the worksheet as well. So it's like half. Distance between two similar atoms. So first off, for diatomic molecule, do y'all know what I mean by that? Do you know what a diatomic molecule is?
Two atoms?
Hmm?
Two atoms?
So yeah, two atoms is a good way to describe it, but it's the two of the same atoms. So for example, a lot of gases, they form diatomic molecules naturally. So like oxygen is a good example of that. O2, you'll see that represented there. But yeah, the definition is basically saying half the distance between these two, which is essentially, you know, about one electron cloud that reaches some point, one other electron cloud that reaches some point, right? So, you know, it could also be considered just the distance there. But I think that's just atomic size is more of a scientific definition there. So yeah, that's all let's talk about that. So let's talk about trends here. So atoms tend to get what as you move down a group? Larger or smaller? Smaller as you go down a group?
Larger. The group is.
Yeah, group. So group as in a column, right? If you go down that column, they get larger or smaller? Larger, right? So they get larger. Any idea as to why they get larger? Can we get a good guess? You also have to answer this in your note in the activity 2, so I just want to see.
More electron field they get, like go to the next ring.
They go to the next ring, okay.
Or the next orbital.
Gotcha. Any other definitions or ideas for that? No? So yeah, Sam, you're correct, but you just need to use the right terminology, right? So each new period starts. So what energy level is 2 on? Or what energy level is boron on?
2,
Energy level 2, right? Aluminum.
3, 4.
right? So as you go down the periodic table, you have increasing energy levels, which means that your radius is bigger. So what I put down for here is just that essentially the more energy levels you have, the further those electrons are from the nucleus, right? So each period, so what I use as justification is that each period starts a new energy level, right? Which is further from the nucleus. So yeah, I mean, your definition was right, it's just putting the terms, right? We're talking about, specifically the main reason why is because you have another energy level, right? If we think about that diagram that Mr. Hobbs made with like the Russian doll diagram, right? We have the 1s, and then you have the 2s right outside. It's just automatically just going to be bigger from that. Alright? So, tricky one here is, what about from left to right across the periodic table? So, do they get bigger or smaller as you move left to right? Smaller, right? Looks like everybody's in agreement there. And luckily you have your graphs to back them up, so if you've plotted the data correctly, you should have a trend of going smaller. Your graph should look like a diagonal going down. Or at least for that like one period, and then it switches and the other one goes down. Right? Or whichever way you use the graph. I put a couple different ways that you could potentially graph this. So it's up to y'all on that one. I guess I need to fill in this part. They move smaller as you move from left to right. Across a period. Alright? So, as you add electrons to an element as it goes across the period, where are they being added as you go across the period? What energy level are they going to be added at? The same one, different energy level? What? Like if I started with lithium, right? And we go to beryllium, we add one electron, right? What energy level is that electron going into? Two.
A different type of
2 levels.
From lithium to beryllium?
No, not for
Yeah. So different type of suborbital, but they're still in the same energy level, right? So they're still the same relative distance from the nucleus, right? Again, going back to the model again, redraw it here. You have the 1s here, and if you have the Russian doll, you have the 2s, but you also have the p orbitals that are like this, right? So these electrons are still in the relative same distance, it's just they're in a different orbital pattern, right? So that distance doesn't necessarily change. So I'm going to put the same energy level. At the same time, the nuclear charge is what? Which causes the electron to be pulled in more tightly. You may not know what a nuclear charge is, but like it's going to get stronger, right? So, what do I mean by that? So let's talk about effective nuclear charge, or effective nuclear charge. So, what effective nuclear charge is essentially you're taking the number of protons of an element, and then you're subtracting the number of core electrons that are in the inside shielding it. So basically what I mean by shielding is essentially you have, let's say you've got an element here. Let's say this is, it's magnesium. Let's say this is magnesium, right? So you have your 1s, you have your 2s, and you have your 3. Or you have your 3 energy levels, right? So you have electrons that are filled here, electrons that are filled here and 2s and 2p. And then you have your 3s electrons that are there, right? So if we're talking about magnesium, we're talking about the effect that this nucleus has on this electron, right? So when I talk about shielding, what's happening here is that in the way of this electron is these electrons from the first energy level, and then these electrons from the second energy level. Does that make sense? So if you're like calculating effective nuclear charge, I'm like, okay, so let's say nuclear charge, we're going to use Z as nuclear charge, Z effective here. I don't think we really talk about this too much in the notes, but if you want to go ahead and just like put a little thing down, because it's not, we're not really calculating too much effective nuclear charge. It's just useful for us as a reasoning behind these trends. Does that make sense? So magnesium here, we know how many protons does magnesium have? 12 protons, right? So how many core electrons are shielding this electron from the rest that are inside? How many are shielding? 10. So effective nuclear charge is what? 2. Yeah, I wrote it down, but yeah, it's 2. And so we really like right now we're only considering just like our S and P's. And that's why we say effective. There's another formula for like the actual nuclear charge, because not all of these shieldings are the same. Some orbitals shield more than others. However, that's not something that you don't talk about here. I don't think you talk about in AP. I think I learned it in inorganic chemistry, which is like a junior or senior level class in college. So you'll not have to worry about the actual nuclear charge, but the effective nuclear charge is nice for us as a reasoning behind this. So as you increase, you have the same distance, but a stronger effective nuclear charge, which means that this positive charge is more strongly attracting that negative charge on the outside. So you end up shrinking the atomic radius. Does that make sense? Cool. Awesome. So I'm going to fill this in. Oh, yeah, I already filled it in. So let me just show you a quick graph just to demonstrate that.
As he's getting that open, remember when we talked about why 4S fills before 3D? Because the 4S penetrates down in closer sometimes than the P's do than the D's do. So when you look at magnesium's effective nuclear charge, if shielding were perfect, it would be a 2. Okay? But the reality, it feels a little bit more than a 2 because the S electron, the 3S electron, gets a little bit closer to the nucleus some of the time. So you might find that actual effective nuclear charge is 2.6, 2.8, something like that, a little bit more. Okay? But it's still going to be way less than 12 because of the shielding by all those core electrons.
So, well, that's the iron one, which we'll talk about. There it is. So yeah, this is just a quick visual, besides the graphs that you already made, visual representation of our atomic radius. I showed this before we left and went back to hybrid, but again, as you can see, lithium, much larger than beryllium, or not much larger, but larger than beryllium, boron, chlorine, carbon, nitrogen, oxygen, and fluorine, right? And again, we can explain that using the effective nuclear charge. Right? And we'll get into the next part of this in a bit. But I don't think we talk about that till ionization energy. So, let me put the notes back on here. Ionization energy. So, actually, let's start with, I think I had you do electronegativity first before ionization energy. So let's actually jump to electronegativity first. So let's just skip to the bottom of the page here. I'm going to jump around here. Electronegativity. So does anybody have a good definition of electronegativity? Do you remember, if you remember from the activity, I put one down there, but I just want to see, refresh your memory, see if we have anything for that.
I don't attraction for a shared pair of electrons when it's chemically combined with another element.
Gotcha, yeah, so that's exactly right. An atom's attraction for a shared pair of electrons when it's chemically combined with another element. Do we have like a super basic, just like, almost like build your own Hobbs definition of electronegativity? No? Idea? It's how much an atom wants an electron.
No.
How much an atom wants an electron. So at the end of the day, atoms that want an electron more are going to have a higher electronegativity, right? So let's talk. So let me go ahead and put the real definition up here. But that's a quick way to just remember electronegativity. Which atom wants it more? You know. So let's see. And atoms. And this will make more sense when we start getting into bonding, although that will be next semester. Because that's when we'll get into shared pairs and how bonding works with that, and why electronegativity comes into play with that. When it is chemically combined with another elements. So, when we did, okay, so y'all did the charts, right? So what did you notice about electronegativity as you went, so it decreases as you move up in a group or down in a group?
Down.
Down. So it decreases when you move down in a group. Alright? And then it increases as you move left to right. So there's your trend for electronegativity. Down in a group, so you're going down, it's going to be smaller. If you're moving left to right, it's going to be bigger. So here's a chart. Do you have it pulled up on your computer, Mr. Hobbs? That chart I sent you. It's like a color-coded, like almost like it's like the heat source tile chart where it shows like which atoms are most electronegative and which ones are least electronegative, right? So I guess in general, so why would we think that, for example, elements on the right side of the periodic table are more electronegative? Do you have examples of that or definition of that?
They're like almost like they're like almost full, but they're not, and they're closer to being full than the ones on the other side.
They don't need as many electrons.
Yeah. They're closer to being full, so they tend to want to attract one more electron, or to become full. So, is that pulled up?
Yep.
All right, sweet. I'm going to switch it here. So, the most electronegative, least electronegative, because of the trends that you learned, may not surprise you. But here's a chart here for you. So, the redder it is, the higher the electronegativity. So, out of this group, which one has the highest electronegativity? Krypton, the highest electronegativity? It's a little bit orange. Fluorine. Fluorine, yeah. So fluorine has the highest, and we can explain that too. So krypton, this is what I was talking about. When you get bigger, it is a little weirder, right? Because these are full, right? These noble gases. But they can still form bonds. Because of how big they are, they tend to have looser electron attractions. And so that ends up meaning that they have some sort of electronegativity. But the strongest here is fluorine right here. What's the weakest out of these? I hear helium. Okay, so besides the ones that have no data,
Oh.
the no data ones don't count.
Like lithium, any alkaline metal.
Lithium is, so which one's the lowest of the lowest now?
Lithium.
Whatever FR is.
Whatever FR is? Yeah, francium.
France.
Francium is the lowest electronegativity, right? lithium 0.098, francium 0.07. Again, that goes along with our trend, right? Because if we go down a group, our electronegativity, what? If we go down a group, electronegativity does what?
Yeah.
Goes down, right? So lithium, all the way down to francium, francium's our lowest.
How does that relate to the size of the atoms?
They're bigger, like they have more electrons.
Okay, so as far as distance from the nucleus, where are those electrons located? Closer or farther away? Farther away. So what does that mean about their attraction? Their ability to attract an extra electron? To get stronger or weaker? Weaker. But long distance relationships are hard to maintain, right? The farther away you are, the less attraction there's going to be. So this trend really is inversely proportional to the size. The bigger it is, the weaker the attraction for that shared pair of electrons.
Yep.
Whereas fluorine, what's fluorine size in terms of all the other atoms?
Smaller.
One of the smaller
It's
ones.
the smallest one, so it's gonna have the electrons being attracted are gonna be closest to the nucleus. And so they're gonna be attracted the most strongly. So the bigger it is, the lower the electronegativity, the smaller it is, the higher the electronegativity. So you can follow the family trends on that.
Alright. So with that, you have a couple of blanks. So that's just filling in this bottom part in here. So we just talked about it here. So francium has the lowest negativity, or electronegativity. Spells francium. There we go. And chlorine, excuse me, my brain is not working. Fluorine has the highest. It goes from a scale from 0.0 to 4.0, with 0.0 being the lowest and 4.0 being the highest, right? That says, we say that, and that's with 1 decimal, right? So technically fluorine would have 4.0, because if you remember fluorine's number was 3.97. So we can round that up to 4.0, but if you carry out the one more, you can 3.97. But that's just if you were slightly confused on that.
Isn't fluorine? Fluorine's the most toxic out of all of the elements too, isn't it?
Most toxic?
Or like harmful to humans.
Mainly if you're talking about hydrofluoric acid, I think is what you're thinking about. So that's when it's combined with a hydrogen, and that acid itself is the most harmful to humans. Even though technically it's not a strong acid, which sounds weird, but you'll get that into that when you get into acid and bases. But yes, it's one of the most harmful to humans itself.
Isn't it like the most reactive element's the most harmful though, generally?
Generally, yeah. If something is super reactive, it's going to be fairly harmful, and we'll get into that. So you actually, when we get to chemical reactivity, which is like in a few seconds, if we get to that, yeah, fluorine's the most reactive non-metal. And we'll get into the most reactive metal when we talk about that. But yeah, if something's really reactive, it means you don't want that to react with parts of your body that it's not supposed to react to, right? Alright, so let's go up to ionization energy now. The last one we did with our graphs, 141, we'll get to some of it. Probably not all of it though. So, ionization energy. Do we have a definition for ionization energy? Y'all, it was in the worksheet. Do y'all remember?
Energy needed to remove electron from a gases.
Yeah.
It is a measure of electron stability.
Yeah, it's a measure of stability. It's the energy needed to remove 1 electron from a gaseous atom. So, just from that definition alone, what do you think, just guesstimating, what would have the least, or the smallest ionization energy?
The elements that would be
A larger element.
Larger elements? Okay.
It's
Least
electron.
Yeah, that's true, larger elements. What about as from left to right. Which ones are gonna have the lower ionization energy?
Left.
Left. So yeah, your general trend is it increases from left to right, and it decreases as you go from top to down, or top to bottom. So let's go ahead and fill some stuff in here. So first, let's fill up ionization energy. So energy needed to remove. Am I not right? Man, spelling is really my biggest curse today. An electron from a gaseous atom, and it is a measure of electron stability. And so, like we said, it generally decreases as you move down the periodic table. Decreases. I said down second, that's why I And again, like we mentioned a little bit there, you said it's bigger atoms, right? So the electron's further from the nucleus, so it means it's easier to remove, right? So yeah. So the electron is farther from the nucleus. And then generally increases as we move from left to right. All right. This is a small blank to right, left to right. My bad. Should have made this a little bit bigger for y'all. So why would it increase as we move from left to right? Quickly. Any ideas?
Electrons got closer.
Well, there's more protons than any electrons.
So what term have we been using? What's on that?
Nuclear charge.
Nuclear charge,
More
right?
effective nuclear.
So yeah, effective nuclear charge, right? Because if you have a bigger nuclear charge, that means it's a bigger attraction for that electron, which means it's less likely to leak, right? So if we look at magnesium, again, 12 easier, or 2 effective nuclear charges easier to remove. And we talk about something like chlorine, chlorine's got an effective nuclear charge of 7. So much harder to remove an electron from there. And again, just from our general explanation of, its stability, if it wants to be full, or it doesn't want to lose an electron if it's getting close to being full.
Yeah.
And we'll go into more of the detail about the sections on that, probably on Friday, so we'll have to watch a video of that. We'll go through the rest of the terms there.